Hello, everyone.
All right. Hi,
Hello,
everyone.
everyone.
Welcome back. As you know, my name is Aroshi Ghosh, and I am the founder of AI Spectra. Today, we have a very special guest with us, Mr. Alex Baretta. Mr. Baretta is an entrepreneur and engineer investing and leading various startups and projects. He's currently leading Tickup AB, a Swedish hedge fund company where he explores the applications of AI and machine learning in systematic trading algorithms. And today he'll be joining us to talk about the startup lifecycle, high frequency trading, and cybersecurity surrounding AI. With that, I will pass it on to Mr. Baretta.
Thank you, Aroshi. I am honored to be a speaker here at AI Spectra, and I hope that my talk will be interesting to you. I expect that you guys are here because you have an interest in startups and the bleeding edge of technology. So I'll be hopefully talking about things that are of interest to you. Feel free to stop me at any time. Feel free to ask questions at any time. This is not a lesson. This is hopefully a conversation, and I'm hoping to get as much out of it. And I'm hoping to learn from you as much as you hope to learn from me. Okay. Now let's see if my presentations are working. Can you see my? Can you see the first page of my presentation?
Yes, we can.
Okay, excellent. So I have 3 topics and a backup for you today. Topic number 1, how to start or not a company. Much of technology gets developed at startups, and startups are really cool and a lot of fun, but there's good ways to think about startups and go about starting companies, and there's really bad ways to do the same. So I'll present you with the two sides of the coin. Then we'll talk about the really cool technology of our decade, which is AI. And there's a lot of bits and pieces of AI, many of them misunderstood. I don't plan to teach you how to do AI, but I hopefully will be able to give you some insight into what the terms mean for real, and not how they're used in the general media. And then we'll talk about one niche step in AI projects, which is very important, and it's the cybersecurity element of AI, often overlooked, especially in the initial days of AI when it was unclear that cybersecurity was a relevant problem. Now it's becoming more and more of a research topic and also a topic in the industry. And finally, I'll tell you a bit about the problem space that I am working in today, which is high frequency trading. And we might get to play with that a little bit. Okay. A little bit more about myself. I'm a bit of an engineer, a bit of a mathematician, a bit of an entrepreneur. I've done all sorts of things, and I've studied all sorts of things. I come from Milan, Italy, and I attended college there at the Politecnico di Milano, where I studied a lot of electrical engineering. And this is what my hometown looks like. It's an old city dating from the Roman Empire, the times of the Roman Empire, with lots of modern architecture and flourishing business and technology. And it's on the back, and you see the Alps, the mountains on the background, where people from Milan have the luck of being able to travel in about an hour to go skiing. And then I spent 1 year in France at the École Polytechnique to study computer science. And that's where I really learned computer science. So if you want to learn computer science, go to France. And it's a really cool university, one of the best universities in the world. A couple of things that I want to point out about the École Polytechnique. 1, the campus, gorgeous campus. I would travel from Paris, where I lived, to the École Polytechnique by train, and the train station is at the bottom of a hill. Then you scale this hill, and it's not a tall hill, maybe, 100 feet. You reach the top of the hill, and there's this huge plateau. It's all green, fields, and it's just wonderful, okay? And then you've got the actual campus with labs. It's a small school, a few hundred students, and unbelievable computer science and physics labs. It's just unbelievable equipment. And then another piece of information that makes this university really, really amazing is its student population. These are my colleagues there. Now, I am an Italian citizen, so I was there as an international exchange student, but the French citizens who were attending school there were all military officers. They were all cadets in the last stage of their training program. They had already done 2 years of service in the French military, driving tanks, or shooting artillery, shooting cannons, all sorts of heavy-duty military tasks. And then they went to school for the last 2 years of their tenure as cadets, studying particle physics, quantum mechanics, theory of holomorphic functions, and other really amazing topics in math and computer science. I was working with these guys, some of the best people I've ever met. After that, 10 years of career in Europe as a freelance engineer doing industrial engineering and computer science. But a lot of what I did was industrial engineering, and I was designing equipment for industrial applications and helping customers who were buying that equipment set it up in various countries. So I would travel a lot, and I had the pleasure of visiting former Soviet Russia. This is a picture of downtown Arkhangelsk, a city on the White Sea, which is a little strip of sea between Finland and Russia that borders onto the Arctic Ocean. I was there on March 21st, allegedly, some say, the first day of spring, but not in Arkhangelsk. Boy, was it cold. And the only thing you could see landing with the airplane was snow everywhere, everywhere. In the US and in Europe, when there's like an inch worth of snow, airports shut down. They had like yards worth of snow and a very long landing strip, and the airplane just landed perfectly fine. And then I moved to Silicon Valley roughly 10 years ago, specifically October 2010. So I'd say a little bit more than 10 years ago now, to enjoy the technology bubble. And I've been on the Silicon Valley treadmill ever since. You'll find that in Silicon Valley, things happen really fast. And so in the last 10 years, I've worked for all of these companies, which is probably a wee bit too many. But like I said, it's just how things are in Silicon Valley. I started out working for Wink, a search engine company. They were trying to be the next Google. They failed at being the next Google, but they built interesting technology, and they were acquired by a company called My Life. Then I joined a company called the Climate Corporation, allegedly trying to solve the world's climate problems, but in reality, using a ton of big data and machine learning and AI to build quantitative weather insurance model for farmers. I was on their quantitative financial technology team, receiving AI models from the agronomy and the climate modeling team. Very interesting technology. The company was ultimately acquired by Monsanto for $1 billion. So a rather interesting experience there. I was the CTO at Lumity, a health insurance technology company where I developed completely new approaches to machine learning, specifically for the insurance technology space. And then I had, what happened here? I had a fairly long stretch of experiences in trading. Shambhala, KCG, and Virtu Financial are 3 high-frequency trading firms. We were building at all 3 companies what are commonly called in the industry trading bots. They're not physical robots. They don't have mechanical components to them, but we think of them as bots because they're machines that interact with other machines and perform actions that have a real world impact. And so, I like to think of myself to some extent as a robotics expert, though in a very virtual way. I've also invested and been advisor for many years at a startup called Zaguro. I was also their virtual CTO for a little bit, hiring their engineering team and architecting their product. And I am now leading the high frequency trading team at a hedge fund called Tickup, based out of Sweden. My team is a virtual team distributed all over the world. I have the pleasure of starting my workday at 4 a.m. with my first meetings with Europe and ending my day at 10 p.m. with my meetings with Asia. So, you know, virtual teams are great. You get to hire the best talent wherever they are, but then you're always on, like it's a 24-hour workday. Finally, I'm working on a startup called Simplectica, my own startup, which aims to make starting businesses super, super easy. So when you do decide to start a company, hopefully by that day, Simplectica will have launched its product and you will become my customers. All right? Any comments or questions so far?
I think one question that a lot of people are having right now is, since you've had the experience of studying abroad, how does education in the EU differ from colleges in the US? And what would be the process for students who want to go to Europe and study abroad?
Okay, so unfortunately, my experience is outdated. Let me go back to that slide. As you can see, it says that I have a 5-year engineering undergrad program in Milan, Italy. Just as I was in the process of graduating, the Italian university system was completely revamped. And instead of having 5-year programs that had the social, that sort of fit the social need of PhDs, the goal of these 5-year programs was to train university professors. Okay, so long ago, we didn't have PhD programs. We didn't have undergrad and postgrad. Basically, high school served the purpose of the American 4-year general ed college. And the 5-year undergrad program was the only college program, and it served the purpose that in the US, a PhD program would serve. So my 5-year program was very, very different from any undergrad program that you have here in the US. Here in the US, you get roughly 50% of your 4 years doing general ed, 25% doing electives, and 25% of your 4-year college program is in your field. At the Politecnico di Milano, I got 5 years of only math, physics, computer science, and electrical engineering. For 5 years, that's all I did. Okay, so it was purely technology and the foundational math and physics and chemistry, the foundational science. Very, very different from here. I think that that model that we used to have was far more valuable than the American education system. For one thing, it was very demanding on high schools. High school students, even coming from vocational schools, some of my colleagues in the electrical engineering program had gone not to the regular high school, they had gone to vocational high school and trained as electricians. They came out of their high school program for electricians knowing calculus. Okay, that's pretty heavy duty. And they knew more calculus than me. I went into my first year of calculus at the Politecnico thinking, oh, I know everything. And the teacher said, whatever you think you know, you don't know it. So let's start from the very beginning. Let's start from what is a number. And he literally built up the whole theory of calculus from what is a number, making no assumption about anybody knowing anything, okay? In 1 year, 1 year meaning one full credit, so 100 hours of lessons, that teacher built up the whole theory of calculus from not making any assumption about students knowing addition and subtraction. Okay, that was sort of the level playing field. Yet, my colleagues who had come out of vocational high school and had trained as electricians knew more calculus than I did. So, and that was humbling. Then I went on to the École Polytechnique. Now, the École Polytechnique, as I said, is a 2-year program after 2 years of service in the military. Okay, so allegedly, that 2-year program happens in the sequence of classes in a student's life that roughly corresponds to, what is it called, the associate degree here in the US, community college, 2 years after high school, allegedly. These guys started, one of the math classes that I took there was entitled Theory of Holomorphic Functions. I will not try to explain what that is, but I guess it doesn't sound like an easy topic. Okay, it wasn't. We studied theoretical computer science. I punted on the quantum mechanics class because I thought it was a tad above my pay grade. I had gone through 4 years of education at the Politecnico di Milano. Okay, I thought that the quantum mechanics class was probably a little too intense for me in my 5th year of college. What I am telling you, I guess, is college education in the US is not quite as competitive as in other countries in the world. So I would recommend to all of you to go to college because it's a social norm. So, go to college by all means, but don't expect that your college education will suffice. You really have to build up your expertise on the side by yourselves, like you guys are doing here. That's exactly what you guys are doing. Aroshi is leading a robotics team. I am sure she introduced herself. She's leading a robot, she was one of the leading members of a robotics team, FTC 8404 Quicksilver. These guys, Aroshi and her team, are studying mechanics, electrical engineering, computer science, theory of automatic control, differential equations. They are years and years ahead of what school teaches them. That's what you have to demand of yourselves if you want to be business leaders and technology leaders tomorrow. It's a hard work. It is, by all means. But all the material is out there. And frankly, good material is far cheaper than college education. So do think of college education as a societal norm. You have to do it. But also think about training yourselves by buying a good book about math. A good book is about $100, rather expensive book. But if you take the same material in college, it'll be, $10,000. So a good book is worth a whole lot more than the college class that teaches that book. Does that answer the question?
Yeah, I think it does. And that actually goes into the whole alumni program that we introduced at the beginning of this event, since it is a little bit harder for some people to know where to look for resources and opportunities. So make sure you stay in touch after the event, and we'll give you resources such as online courses, links to summer programs, internships, etc. So yeah, I think that ties in pretty well.
Excellent. Shall I move on?
Yeah, I think that would be great.
Wonderful. So one thing I wanted to point out about this slide is I've been in California for about 10 years, a little over 10 years. I've been at 9 different companies. Just saying. Okay, I won't say anything more. And since we mentioned Aroshi's interest in robotics, yes, they're really cool. This is a project I worked on. This is not the product that I worked on. It's from a competing firm. I couldn't find a video of the firm that I used to work for because they went out of business. But this is oh, what happened here? That's not what I wanted. Oh, that's weird. I guess PowerPoint does not play YouTube videos. Okay, let's ignore that. Let's move to this version of that slide, which hopefully works better. Can you guys still see it?
Yep, we can.
Okay, it is happening. My computer is slow, but it's getting there. So this is a glass cutting machine. Okay, it's a glass cutting robot. As you can see, it's got something that looks a little bit like a pencil. Okay, it's actually a little like diamond wheel, very small wheel that makes a very small groove in the glass. Okay, and look at the kinds of drawings that this thing makes. I'll show it to you once more. It's drawing circles. Okay, it's drawing circles on the glass with a required precision on the order of 1/10 of a millimeter. This is a motion control application in robotics. This is the kind of stuff that I was working on back in Europe. Really, really cool, a lot of fun. Any question about robotics Any comment here?
I think just to put it into a little bit perspective, a millimeter is about like, I think
One,
1/100th of a, no, 1/10 of a centimeter, right?
1/10
And
of a centimeter, 1/25th of an inch.
1/25th of an inch, right? So if you're going even smaller than that, that's how precise this machine is. So just put it into a little bit of perspective. Sorry, my metric units aren't as great.
So put it this way, when you draw a circle on glass and you end up having to break the circle along the groove, if the starting point and the end point of the circle don't match exactly, you're throwing away the whole big sheet of glass. You're throwing away, I don't know, 100 square feet of glass, okay? Because it will break all over the place. So the starting point and the end point of the circle have to match exactly. Okay, that's pretty detailed, okay? It's a very high degree of precision that you need to achieve. Very different from the level of precision that the self-piloting, autonomous robots that Hiroshi works on are able to achieve. But it's doable, and it's kind of stuff that I was working on. And the math and the physics of robots, of that kind of robot, is very, very exciting, very interesting. So I recommend everybody to look into robotic control in college. And now let me close this. How do I close this? Let me go back to PowerPoint if I can. Excellent. We're back to PowerPoint. Okay, now startups. How do you start a company? How do you not start a company? I don't know that I'll be talking about the life cycle. Hiroshi mentioned I'll be talking about the life cycle. If you have questions about the life cycle, happy to answer them. But I just want to give you sort of the decalogue of startups. What things should you do? Which things should you not do? Startup how-to. The main rule of startups is find a problem that somebody really cares about. Okay, not just cares effectively, but cares economically. Find a problem that somebody is willing to pay for you to solve. It can be a problem for consumers that affects millions of people who are willing to pay $1, or it can affect companies that, maybe it affects only 10 companies, but they're willing to pay $10 million. But it has to affect somebody that's willing to pay something, okay? It needs to be a problem that somebody cares about enough to want to spend money on it. This is critical, right? Startups are not fun projects. They're not your pet project. A startup is a business, and it consumes your time, your employees' time, and it consumes the investor's capital. So you want to make sure that somebody cares about what you're doing. It's not so much about convincing an investor, it's really about convincing customers that you are solving their problem. And if you have to do a lot of convincing, you're probably not solving a problem that they care about. So this is the single most important rule. And then the second rule is find a good group of people. Very talented engineers, very talented management. Product management in technology is absolutely critical. Product management is the function within the company that is responsible for really understanding the problem that people care about, understanding the nooks and crannies of that problem, and understanding exactly what aspects of that problem are worth solving. And then writing out a plan for the engineers to go build the technology that solves that problem. So a good group of people is the most important resource. Funding is important, technology is important, everything is important, but people are the most important asset in a startup. And one critical feature of your team is their ethics. They have to be good, honest, decent people, okay? It doesn't matter how smart somebody is. If they are nasty and mean, don't work with them. Okay, give them a chance. If you hire somebody and then you realize that they're nasty and mean, give them a chance to turn themselves around. But if they don't, you really have to do yourself a favor and do the rest of your team a favor and let them go. Okay, and this happens. This happens all the time. There's a lot of smart people that have a very high opinion of themselves because they are smart, and maybe they have a very low opinion of everybody else. No matter how smart they are, they're not a good fit. They're not a good fit for a startup. They're not a good fit for a large corporate. They just are not a good fit. Third most important rule. You've identified a problem. You have a good group of people that can solve that problem. Now what you have to do is understand the minimum viable product. MVP is the mantra in the Valley. You have to understand what's the minimum viable product. It's a product, so it's something that you build, and it's viable, so it's something that actually solves the problem for the customer, or at least it solves enough of the problem that it has value for the customer, and it's minimum. It's exactly the amount of work that you need to do to have something that's valuable for the customer, and not a grain of sand more than that. If you start solving more problem, a greater fraction of the problem that the customer really needs for them to be able to adopt your product right away, then you're wasting time. You have to build the smallest possible product with the least amount of effort that is valuable to your customer. Okay, that your customer will actually be able to adopt and use. That's MVP. And it's generally the founder's responsibility, the CEO's responsibility to understand what MVP is and be very, very diligent about pruning all of the nice features of the product, all of the nice technological innovations that are nice, but not necessary and not minimum. Okay, why is this so important? Because you have a short time to launch your startup. Startups, and here, this is the life cycle part of a startup. After you present your deck to the venture capitalist and they say, you are awesome, here's my check, you've got 12 months to prove your point. That check is designed to last 12 months. So in 12 months, you have to build a product, launch it, and get enough validation from your customers that your investors will be willing to write you a new check and a bigger one for another 12 months, for another year's worth of life cycle. So effectively, you got about 4 months, 4 to 6 months to build a product. Whatever doesn't fit in 4 to 6 months, you cannot build, period. So you have to be very, very courageous in cutting parts of the product that you really want, that you really like, that you really believe in, but they just are not going to make the cut. Okay? Questions about MVP? This is surprising because this is really the most contentious point in starting a company. It's really understanding what is MVP. The rest is easy. Okay, yeah, I need to have a problem that somebody cares about. Oh yeah, I'll go find some people who are really good. But understanding MVP is really the hard part. So think about it, and we can talk.
Actually, we have a group project at the end of this event, and this is actually what you're going to be doing. You're going to be building a minimal viable product for some sort of problem that you find throughout this boot camp. So start thinking about all the things that Mr. Baretta is talking about, and try to think about how this can apply to the final group project.
Wonderful. Thank you, Hiroshi. And then once you have a definition of MVP, you don't build it. And here's a critical and highly unintuitive aspect of starting companies. The first thing you do after you've decided what product to build is you don't build the product. You build a demo. Why? Because if it takes 4 months to decide what the MVP is, and 4 months to build it, and then you've got 4 months to sell it, what if you realize, after you've built the product, that there's something fundamentally wrong in your understanding of the space? The problem, as you've understood it, is not quite right, okay? You have to tweak your definition of the product, and that causes a major tweak in the product. And sorry, you have to tweak your understanding of the problem, which results in a major change in what the MVP is supposed to be. You no longer have the time. You fired all your ammo, or most of it. Now you're in scrambling mode. You might be able to pull something together, but you will never get back on a happy path. So, not never. There's companies that have taken a big detour and finally they landed on the right product, Slack being an example. But you don't want to be there, okay? And it's out of pure luck that you succeed once you've taken that wrong turn. So the first thing you do is you define the MVP And then you don't build it. You build a demo and you show the demo. The demo has to be realistic enough that you can get really good feedback, right? If the feedback is, oh yeah, it's nice, it doesn't mean anything. The feedback has to be, I want it now, shut up and take my money. That's the feedback you want. And then you have to say, well, I can't give it to you now because it's really not built, right? Let me build it, but I will build it for you in 4 months, you'll have it. So you define the MVP, and then what do? You don't build it, okay? You build a demo instead. Once you're at this point, now you can apply for funding. Now, in some cases, you can apply for funding even before you find a problem, right? If you are a very successful entrepreneur, you're very rich and very successful, and people know you, you can go up to a venture capital fund and tell them, hey, will you invest $5 million in my next startup? They'll say, yeah, sure. That's not for most people, okay? Most people will actually have to go through all this process first and then apply for funding. And then what happens after funding is all the fun. As Winston Churchill defined it, it's blood, toil, tears, and sweat. Okay, startups are the hardest business environment you'll ever find yourselves in. So, I'm crazy. I'm in my 40s. I'm doing startups, way later than I should. If you want to be in startups, do it when you're young. That's when you get the most out of it. And that's when you have the energy to do it. But do expect 10 years of blood, toil, tears, and sweat, and a very low probability of success. So you don't do this. This is not a get-rich-quick scheme. You do this because you're really, really passionate about something. And that's necessary, but it can be counterproductive. Why? Because if you're so passionate about something that you're never willing to give up, at some point you'll consume your whole life working on a project that is never going to be successful. So it's important to be ready to put the blood, toil, tears, and sweat for a few years, but then you have to have the intellectual honesty to step back and say, this is just not working out. I'll try something else. I'll try a different startup, or I'll go into the corporate world. But at some point you have to be willing to call quits. That's very important. Now, you all know the companies that are successful, right? The Googles, the Facebooks, Twitter, LinkedIn. I don't want to give you a laundry list of companies that were successful, but I want to point out a couple of companies just to reinforce a few ideas. One, Facebook. Who's the founder of Facebook? Mark Zuckerberg. But who's the real, who's the person that's really behind Facebook's success? Sheryl Sandberg. So in 2008, 4 years into the life cycle of Facebook as a startup, they brought in a really, really smart and talented woman executive who turned that company from a high potential startup to a really ginormous money-making business. Very, very talented woman, very talented entrepreneur, I would say. I mean, she's not the founder, but you can really think of her as the entrepreneur behind the success of Facebook. Obviously, Mark Zuckerberg is to be credited for, the first 4 years, but after the first 4 years, it was really Sheryl Sandberg leading and being successful. And, she applied the principles that I presented to you. A lot of work, understanding the problem, solving the problem, and making incremental steps to validate through demos that the product is the right one before investing, $1 trillion to build something that nobody cares about. So very much a role model for everybody, but all the more for you because this is a female-centric organization and bootcamp. And I want to point to this company. You probably don't know them. They're called Asana, and this is a picture of the user interface of their product. They went public last year, very successful company. They're coming in to solve a problem that was solved already by a much bigger company called Atlassian, the problem of project management. Project management is a very old problem, and lots of software has been built for project management, and it all is just horrifyingly bad. Atlassian is the biggest company in this space with a product called Jira. Everybody uses Jira sooner or later, and everybody hates it. My company is just switching from Asana to Jira for all of the wrong reasons. Everybody hates it. Everybody hates it. Asana comes along and says, everybody hates Jira. Okay, everybody's using Jira, but everybody hates it. Let's build a better product. What's better about it? It's simple. It just doesn't get in the way, okay? They didn't have a mathematical model of project management. They just went to users and said, what do you need? I need simple, okay? Well, what's simple? I just need to drag a task from left to right to show that it's making progress. Okay, that's what we'll build. They built a very, very small product compared to Jira, far less powerful, but far more useful. So I'm very fond of Jira and of how Jira demonstrates the concept of MVP and demo as being central to a success of a startup. So now we talk about what to not do when you're starting a company. Build cool technology, but also not build cool technology. And we'll get to the whys, but I'm obviously trying to be contentious here. I'm obviously trying to point out the paradox. Have no sensible business model. Okay, startups, like I said, they're not playgrounds. They're real businesses. They need to have a sensible business model. Don't fake it until you get funded. Okay, people have done it. It's never a good thing. It never works out. And don't make it perfect. And like I said earlier, don't spend the rest of your life toiling and sweating and in bloody tears. Okay, now some examples of what not to do or who not to follow. Juicero, the most advanced juicing machine ever. This juicing machine had the same technology that SpaceX uses to build its rockets. Does anybody care? No. Failed company. Don't build cool technology. This lady is, what's her name? Meg Whitman, I think. Very successful business executive. She was the CEO of HP, one of the largest companies in the technology industry, indeed one of the largest companies in the world. And she left HP and she said, what am I doing next? I'm going to start a company in competition with Netflix. And what is my business model? Oh, I'll do some videos. I'll finance directors to create videos for me. No technology whatsoever, a completely trivial problem space, done 1,000 times before, failed company. WeWork, no sensible business model, right? They were subleasing office space. Okay, it's like me leasing a big office building and then splitting it up into small suites and leasing out the small suites. Anybody in the real estate industry had looked at the business model and said, this doesn't make any sense. If it made sense, we who own the buildings would be leasing the small pieces ourselves. Instead, because your business model doesn't make any sense, you will fail. What happened? They failed. Elizabeth Holmes, she was very briefly the most successful businesswoman in the world. Why? Because through fraud and deception, she was able to raise billions of dollars to fund a company that purportedly built technology to do blood tests. Did the technology exist? No. Was she able to make the investors believe that the technology existed? Yes. She was briefly a billionaire, and now she's facing criminal charges, and hopefully she'll go to prison. I don't have examples of make it perfect. I don't have sort of images for that, but I invested in a company that was building an insurance management platform for life insurance agents. The company's name was Shervita. The founder was really smart, is really smart. I like him a lot. Indeed, I hired him at my current company. He was doing a great job of understanding the problem space and defining all the features of the product. He was so interested in making his product perfect that he never actually launched it. He never actually presented his product to a customer. Obviously, that's not going to work, right? So don't make things perfect, right? Perfect is not good. Good is good, but perfect is not good. And then I already explained the idea of not spending the rest of your life in toiling and sweating and in bloody tears. How is this for a presentation about starting or not starting a company?
I think it's really helpful. I think one thing that people don't realize is even the AI Spectra team pretty much went through this process throughout the past like 2 years to get this boot camp started and to provide all these resources and stuff. So definitely this is pretty helpful, and it's something I wish I knew before I worked with the rest of the team to create this company.
All right, Aroshi, I'll send you my advisory agreement after the meeting. The alphabet soup of AI. AI is cool. Acronyms are cool. So there's a lot of acronyms in AI. Let me just present some of the main ones that are most misunderstood. Okay. Hopefully that'll give you a sense for, how to read an article and when to call BS, which is another important acronym to be aware of. The technology, artificial intelligence. What does artificial intelligence mean? Well, today in the industry, it means nothing, right? It means software, right? Anybody that has software that automates something will call it AI. The real AI research is largely in 3 different camps. One is machine learning, which I'll address. One is logic, so thinking and how to apply logic to automate the process of thinking. And another is to try to simulate the brain. Most AI companies, or most companies that claim that they have an AI-powered product, really are just writing software. So don't lend too much credence to the word AI when you see it in a technical publication or in an article on a non-scientific journal. Okay, if you're reading the transactions of the IEEE, AI probably means the right thing. The transactions of the ACM, probably the right thing. If you're looking at, a random website, probably AI doesn't mean what it's not used in the right with the right meaning. Machine learning. Machine learning is most often used correctly. So what is machine learning? Machine learning at its heart is a set of techniques, mathematical and software techniques, that allow you to write examples of a function and allow the computer to build an algorithmic form of that function that you have not coded, but for which you have presented examples. Okay. This definition probably doesn't match your intuition. That's why I wanted to present it. Think of this simple example. You guys know parabolas, okay? From Algebra 2, you know parabolas, or Algebra 1, or whatever. I can give you the function of a parabola. I can say f of x is equal to 3x squared minus 2x plus 1. That's a parabola, okay? Or I can give you a bunch of examples. I can tell you the value of this parabola. Let's take a simpler one. F of x is equal to x squared. Okay, I can give you a bunch of examples. I can say f of negative 5 is 25. F of negative 4 is 16. F of negative 3 is 9, and so on. F of 1, 2, 3. I give you all the examples. If I give you a bunch of examples, and I'm not telling you what function it is, do you think you'd be able to guess that the function is f of x is equal to x squared? Yes, you'd be able to guess. Now, you wouldn't be sure, because obviously I could say, well, no, actually, f of 6 is not 36. F of 6 is 1. Why? Because I get to pick, okay? Because you're asking me and I decide. But unless I tell you otherwise, your guess is a perfectly legitimate guess. Machine learning is exactly what you're doing in your head by looking at the examples and saying, hey, this is really just a parabola, okay? There's techniques to do this sort of systematically, not just guess. These techniques go under the terms of, well, I'll present some of these terms. So let's just move on. Neural networks. Okay, neural networks are a category of machine learning algorithms. Neural networks are a category of functions that have a lot of coefficients that can be tweaked. And if you tweak these coefficients appropriately, you can get pretty much anything out of these neural networks. So they can look like a parabola, they can look like a square root, they can look like a sine, a cosine, they can look like whatever you want, right? Because there's so many parameters that you can tweak. But they're still just a function, okay? It's a function with lots of parameters, and if you find the right parameters, the function will look like the examples. That's all it is, okay? Neural networks really just replicate examples, just like what you were doing earlier with my f of x is equal to x squared example. backpropagation, very fancy term to describe the mathematical procedure to find the correct value of the unknown parameters in a neural network such that the neural network will reproduce the examples that you've given it. Okay, there is no magic here. Okay, it's just a set of mathematical steps that allow you to take a neural network with completely unknown parameters and define those parameters. At the end of the day, what you end up, if I present a neural network learner the example that I was showing earlier, so -4, 16, -3, 9, -2, 4, and so on, all the way to 25, it'll produce a parabola. That's all it does. What is the mechanism through which backpropagation works? The generic mathematical framework for backpropagation, stochastic gradient descent. Many problems that are described as AI have nothing to do with neural networks. They're not even machine learning problems, but they have gradient descent or stochastic gradient descent at their heart. Gradient descent is the idea that if you want the best possible solution to a problem, and you're able to decide how good of a solution any particular possible solution is, and if you can compute the derivative, you guys know derivatives? How many of you have done calculus?
So I think not many people here have started calculus yet, but
Okay.
Derivative is basically the slope of a curve of a function. So let's say you have like a parabola, right? A derivative at a specific, a derivative would be the equation to find the slope at a specific point on that curve. So
concretely, if we are on the downward part of the parabola, say at -4, the parabola is sloping downwards. If you're trying to find, say, a minimum cost, say that the parabola represents the cost of some decision that you may take, and you want to evaluate the cost of, at -4, you could say, well, at -4, the cost is 16, but it's sloping downwards. So if I increase that number, if I increase the value of my decision from -4 to -3, chances are that my cost will decrease. And indeed, it goes from from 16 to 9. So the derivative or the gradient tells you whether the function is increasing or decreasing and in which direction. So stochastic gradient descent is a technique for finding the best solution to a problem by observing in which direction in the space of all possible solutions, the outcome is improving. Okay, so a lot of what's called AI today is really just gradient descent to find the best possible solution among different possible solutions. It takes quite a bit of calculus to understand stochastic gradient descent or to understand gradient descent in general. Stochastic gradient descent or gradient descent in general is at the heart of backpropagation, which is at the heart of how you build neural networks. So, you have to go through quite a bit of math to get there, but fundamentally the message is it's just math, right? No magic. You're not replicating the behavior of the human brain. You're not like a Greek god of the Olympus that's creating mankind out of nothing. You're just doing math, which is neat because math we understand, and there's no magic attached to it, and it can be reproduced reliably. Why is it not moving forward? Okay, some of the applications of AI, or of this broad alphabet soup of AI that you may have heard of. Why did it disappear? Let's try again. LR, logistic regression or classification. Logistic regression is the process of deciding what the probability of an event is. Often you find logistic regression in the internet industry associated with ads. What is the probability that a user will click on my ad, depending on what I know about the user and what I know about the ad? So if I know that a user likes Italian food, like me, and you show them a probability, if you show them an ad for pizza, there's a certain probability that they'll click on it. But if you show them an ad for, I don't know, Kung Pao chicken, the probability is going to be significantly lower because I am not interested in, or not as interested in Chinese food as I am in pizza, okay? And so if the learner can detect that I'm Italian and that the food that is being displayed in the ad is Italian, it'll say, oh, there's a good probability that the guy will click. And if the food, on the other hand, is Chinese, then it'll say it's a low probability, okay? You can do this with any number of machine learning techniques, neural networks being one that you can put to work. HFT, my industry, high frequency trading. We build algorithms that automatically buy and sell stocks. We do machine learning all the time. We do gradient descent all the time. At some level, we really build AI. We really build systems that make clever decisions. They don't replicate the behavior of the human brain, but you have to give them credit for making some smart decisions. CV, computer vision. Hiroshi's team does computer vision for the robot. The robot has to take a picture of the playing field. It has to understand what's in front of it, right? It has to understand where it's facing relative to the playing field, and it has to understand where are the objects that it's supposed to pick up. Computer vision, very important. It may or may not be done with neural networks, right? There are techniques in computer vision that have nothing to do with the alphabet soup of AI technology. Natural language processing. Google does it all the time when it suggests searches for you. You start typing something and it says, well, maybe you're interested in this topic. Well, that's natural language processing. Translating from English to French to Swahili, natural language processing, another very important theme in the AI community. And this is becoming more and more important. Generative adversarial networks are types of neural networks, or actually the combination of two different neural networks that are interacting with one another, that, for instance, is at the base of deepfakes. You're basically training one neural network to deceive another neural network that's been trained to identify something. Okay, so imagine a neural network that identifies people, and another neural network that's showing images to the first neural network and says, is this a person? No. Is this a person? No. Is this a person? No. Is this a person? Yes. Ah, I found an example of a person. Okay, let me learn about it. And then again, at some point, you end up with a generative network that is capable of producing images of people that look very, very real. Okay, dangerous technology, important, very useful, but it brings us to the next topic in my conversation, which is cybersecurity, as it relates to AI. Any questions so far?
I just wanted to mention that actually tomorrow we're going to be having a full session on classification techniques using ANNs and decision tree classifiers, and then another session on NLP. So a lot of the stuff that Mr. Baretta is mentioning right now is going to be applied throughout the bootcamp. So make sure to take some notes and figure out what interests you the best so we can help provide resources for that later on.
Excellent. So I'm not claiming to teach you cybersecurity. I just want you to be aware of some of the issues that the AI community, the machine learning community, is increasingly facing now that this technology is becoming, gradually more and more mainstream. There are technological problems and there are non-technological problems. Let's start with the technological ones. For one thing, you've got to realize that a machine learning model is not going to learn the big picture. It's going to learn the details, and it will use the details to come up with some very clever rules that enable it to answer your questions. But it's still not looking at the big picture. It's still looking only at some very specific details. For example, if you take a picture of Hiroshi and study her appearance, you might notice that there's some very special feature of the corner of her eye that's very unique. And you might say, well, the simplest way to identify Hiroshi with absolute certainty is to look at the 4 square pixels around the corner of her eye. She's the only one in the world that has this very, very special feature, okay? All I need to do is look at those 4 pixels and I can know for sure that it's Hiroshi. That's clever, but you can imagine that there's going to be problems. Okay, what kinds of problems? Model evasion. Okay, if I know that the model is going to look only at those 4 pixels, I can craft my image in such a way that I tweak those 4 pixels and I can make the machine learning model either identify me as Hiroshi or not identify Hiroshi in a situation where otherwise she would have been identified. Okay, so Learning details is not as good as learning the big picture, and yet there isn't a whole lot that we can do about it. Fundamentally, machine learning tends to learn details that are highly predictive of the outcome. And why is this not working? Okay, here it is. So here's an example. This is a data set that learns to identify numbers, handwritten numbers, okay? Somebody has trained a model that understands what pixels are being used by the original model to identify the first picture as a 3. And so by altering very slightly the 3, you and I would still say, oh, it's still a 3. I mean, it's a little fuzzy, but it's a 3. Well, the machine learning model is already misidentifying this as a 7. Okay, and then as we continue down the path of introducing more and more modifications to the original image, it really starts looking like a 7 to us as well. Okay, but because we look at the big picture, the second image still looks like a 3 to us, whereas it already looks like a 7 to the machine learning algorithm. The machine learning algorithm isn't looking at all the pixels. It's looking at some pixels that in the original data set were highly representative of being a 3. Similarly, adversarial examples. This is an example where a machine learning scientist trained a model with pictures, and his model predicts that the picture on the left is a panda with 57.7% confidence. It's a panda, It's not doing a great job. You would hope for a higher confidence. To us, it's clearly a panda, there's no question. But then when you add just a little bit of noise, okay, of specially crafted noise, a little bit of red, a little bit of blue, a little bit of green, in just the right places, and a very small amount of that, 0.007 times that noisy image, the algorithm now says, oh, clearly this is a gibbon. I'm sure this is like, I've never seen a clear picture of a gibbon in my life. Okay, no question. This is an adversarial example. This is a researcher. Again, they have identified what pixels in that image are being used by the neural network, and specifically what features of those pixels are being used to identify a gibbon. And they figured that this picture, that to us looks like nothing at all, nothing meaningful, when added to the panda, makes the panda look very clearly like a gibbon to the neural network. Again, detail, not big picture. It causes trouble. Poisoning. Poisoning is an even more fundamental problem. Think of companies that collect information from users. For instance, Google collects information about traffic lights by sending us reCAPTCHAs. And we dutifully click on the traffic lights thinking, oh, I'm really smart. I'm solving this tricky puzzle. No, we are slaves of the matrix, okay? The matrix, Google, is asking us to train their machine learning model to identify traffic lights. Why? Because Google wants to build self-driving cars, and they need to know what a traffic light is. Well, lo and behold, they've got 7 billion people on the planet clicking on traffic lights all day long. Very smart. Now, what happens if I'm a competitor to Google and I want Google's cars to crash? I'll start filling in the reCAPTCHAs all wrong. Actually, not all wrong, because then they would detect that I am just misclassifying. I have to learn to be wrong just enough to mess with their data, but not enough to be detected as being wrong. Turns out that if I have the ability to predict when Google is sending me a reCAPTCHA to test whether I am actually a human or to train their own model, if I can predict that, and if I can stay under the threshold, I can poison their data set. Okay, think of companies that post fictitious updates on Facebook. We've had news of the Russians manipulating the elections. That's a type of data poisoning, right? Somebody posts data, Facebook updates, images, whatever, that is fake. That gets picked up by the training algorithm and gets included into the model. Poison data, poison model. These are examples of issues that we have with this technology. Generally, about the general issue here is that the model doesn't learn the big picture. It cannot learn the big picture. It learns details. And on top of that, you have to be very, very careful about the data that you use to train the model. Good so far? Okay.
Yeah.
Let me move forward a little more quickly because I'm past my time. Ethical problems. I don't have pictures for this, so I'll just mention them. Racial bias. Machine learning algorithms that handle people's faces may react differently to Caucasians, African Americans, Asians, and so on. Sometimes that's a problem. Sometimes that's not a problem. If you're building an algorithm that predicts disease, or that predicts the efficacy of a drug, well, chances are the efficacy of a drug might be different for African Americans than it is for Caucasians. In that case, it's good that the machine learning model is picking up on that detail. But what if we're building a security camera system that says, well, in all the examples you've shown me, the African American was always the bad guy. I'll predict that the African Americans are the bad guys. It's doing its job. It's not evil, it's just doing its job. Sometimes the problem is not the algorithm. The problem is just that the data presents the reality that we have seen in the past, and we just don't like that reality. In that case, what do? That's a big problem. And fundamentally, it's not a technological problem. If data about crime shows statistically that there's a disproportionate component of African Americans committing crime, any statistical analysis, whether done through machine learning or just by paper and pencil, will come to the conclusion that African Americans are a higher risk group. What do? I don't have a solution for that. Fundamentally, the solution does not lie in the domain of statistics or in the domain of technology. Gender bias, same thing. There was recently an example posted on LinkedIn of somebody who tried to translate from a language that does not have gender a sentence about being cute, and the sentence was translated in the feminine gender in English. The original language had something like "it is cute," and it got translated into "she is cute." And another example where "it is smart" got translated into "he is smart." Again, it's not that the machine learning algorithm is evil, but the examples that it was fed predict that the word cute is used more often with women and the word smart is used more often with men. We don't like that reality, but that's just the reality of the data that we've collected. So what do? Again, the solution is neither technology nor statistics, right? Verbally abusive language. There's a lot of verbal abuse on social media. If you train a natural language model on social media, it will become abusive quicker than you can imagine. Again, what do? Okay, you can't train with real data because the real data presents a model of the world. It presents facts that you just don't like. Then there's the issue of privacy. Machine learning can know more about you than you know about yourself. Do we like that? No. But does it work? Yes. What do? Illegal discrimination. This is another important one. I work in financial services. Okay, I'm very good at building machine learning models to predict the risk of a financial product. Say that I get features that describe a borrower, and I want to predict whether they will pay back their loan. I'll build a pretty darn accurate model. Okay. Turns out, again, that my model will be racially discriminating against ethnic groups that historically have had poor borrowing ability, okay? But my model is doing its job. It's telling me really what is the probability of default. It's not even doing it wrong. I mean, it's doing it right. It's saying the probability of this person not paying you back is X%. And it's the right number, but it's an illegal number because the federal government mandates that you do not discriminate against, ethnic groups, even if the ethnic information is not part of the model, right? You're basically your model correlates with ethnicity. That's illegal. What do?
So I think with all of these examples, it shows how there's societal bias within our everyday communities and how that is reflected within the statistical models that we build because of the data that we use to train these models and all of that stuff. Just to sum it up, right?
That's the end of the meat and potatoes of my presentation, but if I have more time, I will talk about high frequency trading.
I mean, I think we have time in our schedule if you'd like to continue, but that's up to your time schedule as well.
Let me show you something fun. So rarely do you find a job that at some level consists in playing games all day long. Okay, we in high frequency trading play games with other high frequency traders. It's kind of like going to Vegas, okay, and being a professional gambler. Hopefully, we do a better job than professional gamblers, or hopefully, or maybe not. Maybe professional gamblers are better than we are, but regardless, you know, it's a game. At some level, it's a game, and it's a lot of fun. I mean, if you like this kind of thing. The slide that I'm showing you is about a tool that I built called the seer.py that presents like a seer, like a like a prophet. It presents the vision of a day in the life of a stock. In this case, it's a day in the life of Bank of America, and it's May the 7th of 2020. Let me show this to you in real life. Are you seeing my Linux box?
Yes.
And let's see, and I typed my password wrong, so I'll try again. There you go, okay? This is Bank of America for one day. What does this mean? Well, let's zoom out, and then hopefully I'll be able to explain what's going on here. Okay, no, it zoomed back in. Why did it do it? Okay, this is a whole day in the life of Bank of America, okay? The graph starts very early in the morning. I think this is 2 a.m. when the market opens. 2 a.m., the NASDAQ starts accepting orders from traders. And then at 9:30 a.m., when you see all this spike of activity, is when the market really opens, okay? Is when it's officially open. And then there's a lot of activity all the way to 4 p.m. And you see all these black crosses, which means that everybody is going home. You know, it's the end of the day. But there's a little bit of activity happening in the evening for a few more hours until I think about 10 p.m. when the NASDAQ finally shuts down for the night. This tool displays everything that happened on the NASDAQ that day for Bank of America, okay, for BAC. Let's zoom in. Let's zoom in on the pre-market. Okay, this is what happens before the market is officially open. And I want to show the pre-market because it's a bit easier to visualize and to understand. You see here red triangles and blue triangles. Some of the triangles are open. Some of the triangles are filled in. Then you see some crosses. And then you see some green dots. And then you see a blue line and a red line. And then there's a pink line as well, which I will explain separately. So the blue line is called the bid price. It's the price, it's the highest price at which somebody is willing to buy Bank of America right now. Okay, so here at the point where I am positioning my cursor, the bid price is $22.58. Okay, and I can't quite get the right pixel, but it's $52.98. So this is the price at which there are orders that are listed in the market as buy orders for Bank of America. Okay, they're sitting there waiting for somebody to do business with them. It's like somebody with a storefront saying, you know, I'm selling apples and I'm selling apples for $52 and whatever it was, 87 cents or 57 cents. You know that if you want apples, you can walk into the store and buy them for that price. Okay. Now there's many stores and every store has a different price, but at any point in time, there is a store that has the best price. Okay. Now the blue line represents the store that is buying apples. And so you can go there and sell your apples for the price that they are advertising. And the red line is the store that sells apples, and you can go in and buy them for the price that they're advertising. Well, what do you expect should be the relationship between the price of the store that buys the apples and the price of the store that sells the apples? Should one be smaller than the other? Should they be equal? What do you think?
I think in general, most would expect it to be approximately the same.
But not exactly the same. It cannot be exactly the same. Think about it. If there is a store that wants to buy apples, forget about Bank of America. Let's say that somebody wants to buy apples for $1 per pound. And then the next store over on the same street wants to sell apples for $1 per pound. Should they be waiting for customers to come into their stores? No, they'll walk out and meet each other and say, hey, I saw that you want to buy apples. I want to sell apples. Our price is the same. Here, there's a lot of apples here for you, right? They would execute their business directly from, with one another. The only reason they don't do business with one another and instead they set up shop and have a storefront that advertises a price is because the guy who's willing to buy is willing to buy for a lower price than the price at which the seller is willing to sell. So they have to wait. They have to wait for somebody to come along and say, I want apples really bad right now. I'm going to pay whatever. Okay, I don't care how much I'm paying. Give me your apples. Shut up and take my money. Or on the other side, somebody comes in and says, I really need money right now. Shut up and take my apples. And that's why the two prices are different, right? Both orders are sitting there like a storefront waiting for customers to walk in. In one case, the customer is buying apples and paying cash. In the other case, the customer is buying cash and paying with apples. Does that make sense? Okay, so we've got these two storefronts. At any point in time, we've got the blue storefront, which is the buyers. They are buying apples and paying cash. And we've got the sellers. The sellers are selling apples and getting paid cash. The triangles, the filled in triangles, like this one over here, let me zoom in a lot. This triangle over here is an example of a buyer that couldn't wait. They wanted apples real bad, okay? And they said, I'm gonna pay whatever the price is right now. And so they paid $22.65 to get their apples immediately, okay? It's not apples, obviously, it's Bank of America. They bought Bank of America shares immediately. And so the blue triangle is a buyer, but the blue triangle lands on the red line because the buyer is going to do business with a seller, okay? And the term that we use in the industry is crossing the spread. The distance between the blue line and the red line is the spread. Some guy from the blue line walked all the way to the red line and said, I want to do business with you right now. What's your price? And the price was $22.65. Okay? And then you've got people that change their mind. Let's see if I can display one of these things. There's a piece of my Sear system that isn't working, and hopefully I haven't crashed it. But anyway, you see that there's a triangle, an open triangle here at roughly 22.85. And shortly thereafter, there is a black cross. That's a seller, because it's a red triangle, so it's on the sell side of the market. It's a seller that wanted to sell at 22.85, and then shortly thereafter they changed their mind. They said, no, maybe not, maybe later. Okay. Now, what is our business as high frequency traders? Our business is to put in the orders. It's to file orders that either become open triangles on the bid side or open triangles on the offer side, or filled in triangles. Sometimes we go to the other storefront and say, hey, I want your product right now. I want to buy Bank of America right now, or vice versa. I want to sell Bank of America right now. Give me your money. And we place these orders by inspecting the whole market and understanding where people are placing orders, at what prices are they placing orders, how big are those orders, why are they doing that? Like, why is this guy wanting to trade initially at 22.87 and then 22.86 and then 22.85? And what can I glean about the future evolution of the price by looking at these orders? as you can imagine, there's a lot of opportunity for machine learning here, and yet it is a very, very hard machine learning problem. The hardest I've ever faced. You will learn about classifiers. Aroshi, I don't know if you will present the area under the receiver operating curve as a quality metric for a classifier.
We use the confusion matrix for the accuracy test and stuff, since we don't want to go too far into the mathematics in the 2-day boot camp.
Okay, got it. So I will talk about this metric of quality for classifiers. It's called area under the receiver operating curve. Doesn't matter what it is. The point is 0.5 means your model is a coin toss. It doesn't know anything. Below 0.5, it means your model is wrong, like really, really bad. Above 0.5, your model is doing something right. But again, 0.5 it's a coin toss, okay? So you want to be significantly above 0.5 for your model to really be good. But 0.9 would be a good model. In financial services, specifically in trading, when we get a classifier that ekes out a performance of like 0.53, we're kind of happy, you know, and it's still hardly better than a coin toss, just very, very slightly better than a coin toss. It's really hard to do machine learning on this type of data. And I crashed my seer.py, so, oh, no, maybe not. Maybe it's still here. Now look at the level of resolution in time. And I can keep zooming in and zooming in until, look at the millisecond. Well, this is still in the time scale of seconds. Unfortunately, it's being really, really slow, but I can keep zooming in and zooming in and zooming in until at some point I am looking at nanoseconds. Look at the number that increases at the bottom right of my screen. That's nanoseconds. I'm looking at events that are happening on the time scale of nanoseconds. Let me show you just one more thing, and then I'll leave you guys to the rest of your activities. This is the bulk of the trading activity from 9:30 to 4 p.m. Here, the market is far more active. As you can see, there's orders that are being placed and canceled all day long. Now look at how a price change happens. Okay, now we're zooming in on a single price change where the price of Bank of America increased by 1 cent. Well, maybe a little bit more than 1 cent here, but it increased by a very small amount. And actually, let me take a step back. Look at all the activity that happened in the market at the time of that price change. People started betting down here at 11:01, 4 seconds, and 11 milli at around 550 microseconds. So 11 milliseconds and 550 microseconds. They started betting, oh, this is something is telling us that the price will go up. And so you start seeing cancellation up here, crosses, meaning somebody who was previously a seller is saying, no, I'm not going to sell at this price anymore. I'm going to sell for a higher price. And the buyers are trying to buy as much as they can. They're putting in these triangles that represent orders to buy. And more orders to buy, more orders to buy. Some cancels, some crosses. I'm not going to explain the crosses because that gets way, way too complicated. And then the intensity of the action becomes even higher. And you can see sort of a storm of activity happening here. Again, look at the time scale. This whole price change happens in a time that goes from 12 milli, 216 micro, to 12 milli, 243 micro. So this whole thing happened in 37 microseconds. All this activity down here lasted 37 microseconds. That's the time scale that we're playing at. That's all I have for you, ladies. I'm open to questions.
I think that was a really great presentation. I think we have some time for questions. I think if we say hard stop at 11:30, if that works with you, we can just move on to question segments. So if you would like to raise your hand and unmute and ask your question, feel free to start doing that now. Or if you would like me or another team member to read out your question in the chat, start putting that out. But just to start off the discussion a little bit, so we had a couple of questions where it's like, for students who are interested in learning more about AI and how it can be applied to finance and stuff, you mentioned earlier that a really good mathematic book or any book in general for that specific field is a lot better than like doing a bunch of courses in college where you spend so much money, right? Do you have any place where you specifically go to find these books, or do you have any people that you would say we should check out if we're interested in studying a little bit more about high frequency trading or just AI in general?
So the first place to go is the Coursera machine learning class by Andrew Ng. It's very introductory. The material is not overly complicated. Now, he does use calculus because you have to. I mean, you just have to. So there is a little bit of calculus, but it's really simple calculus. And I think it is approachable by a high school student. It's very good material. It's introductory. So it's, don't expect to become a master of machine learning with that one class, but it's very insightful, right? It really allows you to understand what's going on. Once you're past the math hurdle, then the Bible of machine learning is the Elements of Statistical Learning by a gentleman at Stanford called T.B. Shirani, if I remember correctly, ESL3, T.B. Shirani. T.B. Shirani. And the book is called Elements of Statistical Learning by Hasty. Hasty is the first author. Hasty, T.B. Shirani, and Friedman. Okay, this is available as a PDF. It's also available in print. But I always have a copy of the PDF on hand as a reference. Where's the chat window? Everyone, this guy. So download a copy. Don't be ashamed of yourself if if your level of math is insufficient for you to be able to work through this book, but it sets the level of math that you need to understand in order to do machine learning. Machine learning is deeply rooted in probability theory and statistics. Unfortunately, I have to say that statistics as it is taught in high school, as it was taught to me in high school, is counterproductive. Right? It really just made me think, wow, this thing doesn't make any sense. It wasn't taught well, and it can't be taught well, unfortunately, because statistics is based on probability theory. Probability theory is based on integration theory. Integration theory in this country is typically taught as a post-grad class in a math master's program. So there's a ton of math that you really need to study to get the most out of machine learning, to understand the theory behind it. But the applications are relatively easy and approachable. They do require calculus. So with calculus AB, or somewhere between calculus AB and calculus BC, you should be able to read and understand much of Hasty's book.
All right. And then another question that I was getting in the chat was actually, how do you say students should go about doing research projects in the summer? Do you recommend people go through formal internships, or do you think that creating a project yourself and finding an industry mentor does exactly the same work and is equally beneficial? What are your thoughts on that process, since I know a lot of people are going to be going into that soon?
So I have a recent proxy experience in this domain through my son, Andrea, who for you ladies is also on Aroshi's team. He was looking for a mentor, not in the industry, but in the academia, for a research paper that he's been working on. And he could not get anybody in the academia to even reply to his emails. I find that this is very uncool. If somebody reaches out to me gracefully saying, hey, can you please help me out with this? Can you please, do a talk like Aroshi did? I always say yes, right? Because I try to be a decent human being and I try to help people out. So recently I had a gentleman reach out to me saying, I work at Costco, I've not gone to college, but I'm really passionate about computer science. Can I interview with you? And I said, look, I mean, you're coming from very far. I think you may need a little bit more education, but I'm happy to mentor you. And he sent me some sample code. Turns out he's really, really smart. I mean, I'm surprised. So I'm now facing the challenge of, do I really interview this guy who is clearly, not qualified from an academic perspective? But I'm the type of person who is willing to at least give people a chance to prove themselves and help out, okay? Most people out there don't. I don't agree with that, but it's just a sad fact of life. So if you're passionate about a research topic, I'm not entirely sure about this, but my recent experience would lead me to believe that the best course of action is for you to become a world-class expert in that field. Very narrow field, right? It can be just one little quirk about a broad field, like one little problem. Become an expert, do your research, and publish it. Publish a blog. Publish, an article on, I don't know, Wikipedia. No, Wikipedia is not publishing original research.
And stuff like that.
Publish it somehow, but publish it in your name. Just be courageous and publish. Now, because you're not publishing on an academic paper, there's less chance of being ridiculed than if you were to publish on an academic paper. So it's less risky, but it puts you out there. Okay, and people will look at your work and say, hey, this lady or this young man actually did something really valuable, did something smart. GitHub is a great place to publish your work, right? If it's software, right? If it's a paper, then a blog might be better. But if you're writing software, for instance, you're building a novel machine learning algorithm, publish it on GitHub. People will, or at least may, look at it and say, hey, there's some really smart, some really good insight into this project. The person who wrote it is really smart.
Yeah, and that kind of ties into, so AI Spectra, we do have our blog and publication site where you guys can take these projects that we're doing at this event, take it a little bit further and write a research paper or write about your journey through building this project, right? And just having this small amount of publicity, even when you're applying for other things, you can link to these things and show, hey, I've done this kind of work. I've published it in this publication. I've had people read my stuff, right? And it kind of gives you a little bit more credibility than just saying, oh, I did research here, but I don't have a specific place where you can see it and stuff, right? So highly encourage, if you guys do end up doing these projects, submit it to our blog, submit it to other people's blogs, all of this stuff. All right. With that, I think that is the end of our speaker session. Thank you so much for joining us today, Mr. Baretta. We were really excited to hear your talk. And with that, we will move on to our next session. I will send you an email with other things later on. All right. See you.